we can compress this image, so that again, compression is because we want to send as much as information possible in very less number of data points. Okay, so that's the idea. So we want to do image compression here. Now the question is, how will you treat this data matrix? You will treat it as a matrix. Okay, so what I mean is that you have an image here. Okay, so I represented it as a matrix. There is another way you can do it, is this as a vector. Now, if I want to write this data matrix, what I have to do, I will just write it as a vector. Now this element I can keep here. Now I have a choice, but usually whatever choice you use, just be consistent there. So probably second element I will put here, this one. Third element here. Then fourth here. And I will just keep on doing this one. So is there, the question, first question, is there any data loss is happening? No. Okay, so because each data point is preserved here, each data point is preserved here. So whatever information is available, I haven't deleted or anything I have done with this data point. Okay, so this is fine. So now, which one do you think is best here? I mean, I do not know, but just think about it, because I do not know how to. Is there any comment possible? I mean, Veena sir, commenting is, I think, not possible, no? Anyway, okay, so just think about it. Will you treat this data matrix or this image as matrix or vector? Please remember that there is no loss of information at all at present. Okay, so same data points are available here, same data point is available here. Okay, so what's the, so now there is a problem here. Okay, now what is the problem? Okay, normally in machine learning also, people, if any image is there, sometimes, or earlier it was very common that people used to just write it as a data matrix. But just have a look very nicely, means a very attentively, is that if I, so this pixel is there, let's say this is my central pixel, and this one pixel here, 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 one pixel here. Okay, now this point, which is center of all this surrounding pixel, is having correlation with all of them. Agree? So it is having correlation with all of them. Now, when you write, so this is the natural form of the data, please. And when you write it in vector form, this correlation is broken, because one, this can be here, and so this top three will be there, and then so this entire correlation and its direction and all those things is lost. When it is like that, this is correlated to this one, this is correlated to this one, this is correlated. So something, some kind of this type of map you will get. And if it is a lot of points are there, then there will be some, so it will be a long edge here. Okay. So still the correlation is still there. Please remember, there is no data loss. The main problem is that when you write it in this one and in this matrix form, this particular correlation which was available in front of you is little bit more complicated now. Okay, so please remember that here it is just like a very simple correlation which you can probably see or all of us can see with our eyes. Here the correlation will be this star is correlated with some 2n plus L element or something like that. So you have to find a relationship there. Okay. So here it was a immediate neighborhood kind of thing. Here you have to find a formula, please. Hai na? So when you convert this one into this one, so there is a formula here. Okay. So for example, this matrix can be obtained from some function and then this vector, okay, which is invertible. Okay, so this is the main issue. Okay, so now if you do data processing with this particular v, the long vector, what will happen? To find this easy correlation, you have to first find this r. And that's the problem. Because why it is a problem? Because if you put it into a machine learning algorithm, machine learning has to learn this particular r function, and that's where it gets complicated. Now things are very easy. I mean, if you put in the natural form of the data, but if you just do some kind of formatting or something, then although it is an invertible formatting or kind of thing, but machine learning has to learn that particular formatting for you. And that's where you're even using machine learning or something, then your uh, this the neural net, let's say for assume neural network, so you have to train little bit more, you require lot of little bit more edges, more layers and something like that one. Okay, so please, so the basic thing is, we treat our data in the natural format, please. Hai na? Okay, so this I will explain again with 2 and 3D example. And if those who are mathematically inclined, you can just see that a matrix is there, how to compress. We can use singular value decomposition algorithm to do it perfectly, and there is a perfect answer for this particular. So if some matrix is there, how to compress singular value decomposition is a well-known algorithm there. Although numerically there are some issues with singular value decomposition, but people, so there are some alternatives there. But in principle, singular value decomposition do the task. But if you convert into a this entire matrix into a vector, you can clearly see that this you cannot apply singular value decomposition there, because this vector will have only one singular value. Okay, so this is those who are mathematically inclined, but the first explanation is a generic one, which I think is a little bit more easy to understand, but uh, the mathematically precise answer also I have given to you. Okay, so now same thing. So now what we have is, instead of 2D data, I have 3D. So MRI, all of you know that it is a 3D data, sequence of images will be there. Okay, so you can clearly see. I'm just playing it. Okay. Okay, so here what we have is three-dimensional data. Where is the third dimension? Okay, so one dimension is this. Let's say this is X, this is Y, and the third dimension is this time. Okay, so now to give any index, you need three indices. Okay, so basically X direction you can give how much in this direction, how much in Y direction, and how much in T direction, and then you can probably locate any pixel very perfectly. Okay, so this is a three-dimensional or multi-index data. So why it is multi-index? For example, a data point here A, I need three indices. So one will indicate this IX, another will indicate IY, another indicate IT. Okay, so but probably IJK. Okay, and again the aim is data compression, please. Okay, so in earlier days of signal processing, people used to spend lot of time. Video processing. People used to spend lot of time whether there are repeated frames and all those things. Some algorithm they used to check whether there is a repeated frame or what is the frame which is common with the previous one, how much common it is, and they used to work on the differences and all those things. Okay, so that you are doing it, please. So please remember. Okay, so we are doing it. There is no you can say a mathematical approach which is directly giving me that okay, this is the best possible compression of the video. We are trying to see the frames which are common, or we are checking with the error, and then error means basically the difference with the previous frame, and then we are doing it. Okay, so that's how video processing used to do. But the main algorithm here, or the main objective here, is that can we do it in a perfect way, just like singular value decomposition? Although numerically there might be some issue, but is there a mathematical way where I can just compress a video just following some mathematics rather than just looking at frames and all those things? Means instead of applying some kind of algorithm, or you can say some sequential steps, I just want to let mathematics decide what is the best approximation for me. Although for two-dimensional thing, means for matrix thing, singular value decomposition is the best, and that's the aim. But later on you will see that there is a problem in going beyond two dimension, and mathematically still people do not have a perfect answer. Even people have proved that there is no best answer, but some approaches are there. People mean we can do in little bit better manner. I will show you the simulations also. Okay, so the question is how to compress video. For example, this 3D MRI data. Uh, Singular value decomposition is a good approach. I mean, this is just a one question. So when I asked this question in one of the class, okay, so some of the students they ask me that why we cannot do, for example, the video means it is a sequence of frames, no? Okay, so why we can't do SVD here? I know that okay, I do not have a perfect answer for 3D. Okay, but I can do singular value decomposition for matrix or a given frame, then singular value decomposition here, singular value decomposition here. So all of you know that this is not a perfect answer, because if all the frames are similar, then I am just repeatedly doing same SVD again and again. Okay, so what I want to say is that okay, I so if the frame is repeated many times, then I am doing this SVD again, SVD again, SVD again. So I need some approach, a mathematical approach, which should identify that okay, all of them are same or similar. Okay, so what if this matrix is very close to some delta here? Although SVDs are very sensitive to this type of changes, but let's say this matrix and this matrix are almost same or same data, only some noise difference is there. So then, or probably in time domain they look same, but again when we are checking, we are not doing only, means we are doing only in time domain, that whether this frame is similar to this frame or not. So let's say if they are similar in some other domain, in all those things are there, means which we do not have a perfect answer here. Okay. So to have a perfect answer, first I have to do what? I have to treat my data naturally. Means just we will treat this 3D MRI data only. So what is nature? How nature has given this data? It is just sequence of frames. Okay, so I will just take this entire thing as my. So in case of two-dimensional, I will take this matrix as my entire data. Now in this case, I will take this entire thing as my one mathematical object. Now, what is this mathematical object? There are many names to it. Means people call it as multi-index data structure, NV array. Some of the people call it as tensors. Okay. But basic thing is that it is a three-dimensional structure of data. That's all. I mean, if you know tensors, then probably it is easy. But if you do not know, it is nothing but three-dimensional or more dimension. Sorry, n-dimensional arrangement of data. Okay. So three dimension, which because I can plot, so this is when people call different modes, names are there, but do not worry. Means you can call this as mode 1 and this is mode 2. So this is mode 1, mode 2, mode 3. So X, Y, Z direction basically. And if it is three-dimensional data, all of you know that you will need three indices. Okay. And a particular pixel can be achieved by just looking at that particular, let's say, in this candidate, and then we just assign some value, pixel value there. Okay, so in case of n-way array, we will have n indices here. Okay, so that's what where one of the basic thing is there. So if your data structure, so what is the summary here till now? Summary is very simple. Oh, 1 second. Okay, so what is summary here till now? Summary is that use the data as much as possible to the natural format. Okay, it may leads to a little bit complicated mathematics, but we will not worry about that one. If possible, we will try. Otherwise, we will go back to our method which we know. And a three-dimensional or n-dimensional arrangement of data is called as n-way array, multi-index data structure, or tensors. Okay, but please now little bit mathematics here. So there is a means if we arrange this data in three-dimensional format, it is very easy to see. There is no problem at all. But to do mathematics, we have to resort to something called as multilinear functionals here. Okay, so what is multilinear functionals? So multilinear functionals are, no, I will explain. We will understand this one and rest of the thing we will try to avoid. Okay, so any tensor which or any three-dimensional arrangement of number, so this entire thing can be represented by a multilinear functional. So what is multilinear functional? All of you know linear, I hope. Okay, so this entire tensor is, let's say, T. Let's assume that it is some TM or T data. Let's make it. So this entire three-dimensional arrangement is TD, and there is a multilinear functional T X Y Z. But first, I have to define you what is multilinear functional. Okay, so multilinear functionals are very simple. What it do is that, so T X Y Z is there. So what you can do, you just fix this one, Y and Z, or apart from one, just fix all of them. Then this entire function will become a linear function. So all of you know linear, no? So basically what I want to say that alpha x1 plus beta x2 at a given yz, it will be alpha t x1 yz plus beta t x2 yz. Okay, so this is the property or the linearity property which we have seen in our signal system course many times. Now, this is only even and this thing should work with each of the arguments. For example, t x alpha y1 plus beta y2 z will be equals to alpha t x y1 z. So I have to just fix 2 and the third one will be linear in nature. Okay. And similarly, you can do it with, so what we can prove is that there is a unique three-dimensional data. So this and so there is a three-dimensional data and a one-to-one correspondence between this one multilinear functional and this three-dimensional arrangement of number. So what is the advantage? Advantage is what is multilinear functionals basically means the output is always a real number. Okay, so that's why people call functionals instead of functions, because it is just output is always a real number. Okay, so that's why people just call it as functional. Okay, so now what is the advantage? Advantage is that once I write in this algebra format, now there is an advantage. Means I can now do differentiation, integration, or whatever. Here it is just a data format, and I do not know how to deal with this particular thing. Now what I have done, I have written in a little bit formula kind of thing. Now any differentiation or something is needed that I can do. Another advantage is that it gives you little bit compact representation than this particular three-dimensional arrangement of numbers. Okay, but otherwise there is a one-to-one correspondence. So how to get this correspondence means what I will do is that I will just give, for example, to get the first element here, I will input the first standard basis of this XYZ. So what I will get is that uh, T data matrix that in this one entry. Okay, this to get the first entry, for example, this one. I think I represent it is a W11. So what I will do, for example, tensor E1, E1, E1. E1 is the standard basis. What is the standard basis? Please 1000 something. 100 100 something. Okay, it will give me 111. If I want to get, let's say, this one, so it is mod 1. So mod 1 is here. So mod 1 second element. So what I will do, I will just change it to 2. So it will become W22. W211. Okay, so very simple till now, no complications apart from this multilinear thing. And why we are doing it? Just because we will have a good algebraic formulations. Okay, now we can see a lot of advantage here. So tensors, for example, means are generalization of this n-dimensional arrangement of numbers. So one-way array is basically vectors. Two-way array is basically a matrix, and n-way array is basically means anything apart from means all of these things are means vector matrices are tensors only, but apart from anything above 3 and above 3, so anything above 2 basically people normally call it them as tensors. Okay, now it says a beautiful structure here, so we can see that it has some kind of vector space structure. And now what is the advantage of, you may ask that, oh, what is the advantage of having vector space structure? So the advantage is that you can have basis. Okay, so that's the main thing here. No, means whenever we study in linear algebra or anywhere, why we want to study vector spaces, even in electronics and anywhere, the main advantage is that we will have a basis. And what is the advantage of having basis? So you will get a representative vectors for entire set. Okay, and any element you can construct from those basic set. Okay, so that's a huge power you will see in algorithm. So that's why, so it forms a vector space structure. So that's a nice power we are getting. And there are many representations here. Okay, so let's do not uh, probably only one thing we will just, so multi-array, we all of us know. Multilinear functionals also, I told you that if you put E1 here, E2 or E1 here, so all of these standard vectors, you will get a tensor representation, and you can see, just have a basic look here. So it just says that x1, so x1 vector, lth element here, so xl. Okay, so this x1 vector is there, and in x1 vector I have taken the lth entry, so that is there. Okay, so now if you see this product, what is this? So you can just see that it is some element or some variable x. It is some variable x. So different type of variables are there. Okay. So different types of variable, but these variables are getting multiplied. Okay. And that is again one of the biggest advantage of this tensors, that they represent our data in a non-linear fashion. Okay, and all, if those who know machine learning, they know that what is the advantage of having non-linearity. Now the and tensors is are somewhere in between linear and non-linear, so you can see that some kind of non-linearity is there, but because only one power of this x variable will be there, so you cannot have power more than one here. Okay, so you can have only, so that's the issue here. uh, but otherwise, apart, it's not perfectly linear representation, it is not a perfectly non-linear representation, it is somewhere in between. But then you may ask why you want to use this tensor representation. The thing is, all this tensor thing what I am explaining, you can do with sorry, with matrix algebra. I mean, that's the advantage here, please. Hai na? So uh, anything related. So what is the advantage? Again, it is difficult. If it is difficult to understand, just remember one thing is that tensors are a nonlinear representations lying somewhere in between matrix algebra and nonlinear thing. And nonlinear thing are computationally very high, computations are required. Matrix algebra, all of us know that it is matured, or all of you know that linear algebra subject is so highly researched that now almost all libraries or fast libraries are available. In fact, one of our student was working in something related to some hardware problem, and some linear algebra function was giving him some little bit slower results. But then I suggested him to use linear algebra library designed for that particular hardware, and the results were little bit. You I mean I mean he was surprised, but I was also surprised that the result, the libraries are so much optimized for that particular hardware. Okay, so that's the level linear algebra people have researched upon. Okay, so it is not like that one library is available in the entire world or one type of library. Whatever hardware you have, highly optimized non linear algebra libraries or matrix algebra libraries are available. Okay, and we want to leverage on that particular, we want to use that particular thing. So that's why tensors are useful, because they use matrix algebra only for their calculation. They do not go into that nonlinear approximation and all those stuff. Yet they are a nonlinear representation. Okay, so a kind of, but the downside is that they are not perfect nonlinear representation, because you can see that you cannot have more than one power here. Okay, so this I think this vector space structure I have already, inner product also you can define, and once you define inner product, you always have Frobenius norm, which is nothing but again, these are very simple thing. So whatever data matrix you have, or whatever tensor you have, just take all these data values of the tensor, square them, and sum them. So that is Frobenius norm. So it is basically a fancy way of saying root mean square thing. Oh, I haven't done the mean thing here, but root and square and then root. Okay, so if you read any tensor document, now please things will be easy. What I just want to summarize till now. So what we have done. So tensor is a multi-way or multi-index representation of data, or more than two-dimension arrangement of data, multi-dimensional arrangement of data, and we can represent them with a kind of special function which is called as multilinear functions. Okay, that's the thing you that is the take home thing, please. And so if you are not able to understand till those things, do not worry about it. Now comes the very fancy stuff, and they are very useful for the tensor calculation. You just read any paper on tensors, these things will be there. I will explain them in as simple as possible. So for example, earlier we had three-dimensional arrangement of this data, na? So this type of these things are there. But what I will do, I will just fix one of the variable. So for example, one of the indexes, or I1, I2, I3. So I will fix this I1 here, for example, 1, and then rest of them are varying. Okay, no, sorry. In this case, in fibers case, what I will do, I will vary only one, and rest of the two. So I will vary on fix. I will fix I2, I3, and sorry, I1, I2, and I3. Okay, so I will just fix. Okay, so I will just fix I1 here, and I2. Only I2 is varied. Okay, in this case, I will vary. Oh, sorry. In this case, I am just wearing. I just so this case I just explained for this one. It is basically fix two and change one. Okay, so in that case, you will get not only the data points, but you will get columns of data points. Okay, so these are called tensor fibers here. Okay, now you can. You got the tensor fibers. You can just arrange in some order here. Now this order again is doesn't marry doesn't matter here. You can arrange them in any order, because anyway it doesn't. A lot of people have different types of order here. But why we do this one? Because in some projections and all those things, these things are needed. But tensor folding and unfolding, it is one of the common operations people do in tensor algebra. So for example, these fibers are there. So I just arrange them, first one here, second one here, third one here, and something like it. Depend upon the which rule I am following here. Okay, and to use tensors, for example, now Python libraries are also available, but for MATLAB, Tensor Toolbox is available. You download it and you can use it. In Python, I think you can represent directly in PyTorch and um, TensorFlow. So now in slices, I just fix one and change rest of them. So I will get little bit more bigger data set, and that's what people call it as tensor slices. You can just see that it is, earlier I was just getting columns, now I am getting plain kind of structures. So these are easy thing. Even if you do not remember, just remember that if it is a three-dimensional structure of data, you can arrange them in lines or in a planes. That kind of stuff. This is there. But this entire exercise we were doing to do a matrix tensor and matrix multiplication. And now I will not explain the definition because that's not the aim here. But why we want to do it? The main thing here is that we want to use projections. And those who know, who studied signal processing, they know very well that projections plays a very important role in any signal processing activity. Okay, and that's why we need to define tensor matrix multiplication. It's not very hard. It is basically, if I want to uh, do some matrix multiplication, I have to just multiply in one of the dimension here. So it's very easy in the sense I will explain here. Okay, so this three-dimensional arrangement of this thing is there. Now, if I have to multiply matrix, I have to multiply, I can multiply here. So then it will be multiplied with this one, and the same matrix will be multiplied with the slice before, behind it. And now if I just multiply in this direction, the same thing here. So now, but I have to see the slides from some other direction. And same thing here. Now, if I want to multiply, so I have to multiply in this direction, and then I have to take the slices accordingly. Okay. So that's why, and for a matrix multiplied with a tensor, let's say third order tensor, then there are three ways to do the matrix and tensor product. So so I can multiply in the mod 1 direction, I can multiply in mod 2 direction, I can multiply with in mod 3 dimension. That's why this is called as mod n product. But again, going from this instead of math point of view, just remember that it is needed for special purpose, which is called as projections. Okay. Similarly, we can define tensor and vector multiplications. So now we have, yeah, there is a problem. Means all of you know that once we have some projections, so we have to discuss about what is orthogonality here. So for orthogonality, we instead of we define tensors in little bit. Okay, let me explain in this way. I just want to avoid the minimum terminology here. So now, so inner product is 0. That is very simple. Okay, so if orthogonal, inner product can be 0. Okay, but in some of the special cases, because it is not only one vector and another vector which is getting inner product. In tensor case, it is dimension wise, there is some issue is there. Okay, so each dimension is having some, let's say, representative vector. Then the multiplication, if one of them dimension is orthogonal to another dimension, then it leads to another type of orthogonality. Means if we want all of them to be completely, means each dimension is orthogonal to another dimension, then it is called as completely orthogonal. Let's do not worry about this one. So there is a rank issue here. I will not explain this one. Okay, so let's. So there are two types of rank available. So what I can do here is that one is the actual rank which we know from matrix thing. Okay, so I will just divide this in smaller matrices of rank 1, and then whatever this sigma is getting, I will just say that rank. But there is a problem with this rank, so we cannot define it properly above dimension 2. So for matrix it is perfect. For tensor, means about 2, it is not perfect at all. Okay, so what we do is basically we convert, or we will do the matricization in every direction. So for example, a tensor is there. I will put this here. So I will do matricization in each direction. So one way is to write a matrix this way, another matrix is this way, another one way is this way. So I will just use all these three dimensions to do the flattening of my tensor, and then I will find the rank. So each direction I will get different ranks. So that is called as model rank. Do not worry about it. There are so this basic problem is that I cannot define rank properly. So I go for matricization, and all of us know that for matrix rank is perfectly defined. Okay, so now this leads to different problems, but I want this. So this example is there, but don't again. I want to skip it. This just says that rank problem is not a perfect problem as we see in the matrix case. So for anything n greater than 2, there is some problem here. So we cannot define rank properly. So we have different representation. So this is what a normal rank decomposition will look like. But what I will, or what we will do is that we will make a matrix of the tensor, and then we will do SVD or some kind of orthogonal decomposition, and then we will make some vectors here. Okay, so just bear with me for 2-3 minutes, then we will I will stop the theory here. Okay, so now please, so this is the so if you want to apply tensors in your somewhere, then this higher order SVD is one of the algorithm you will apply, and it's very simple. So just forget about all the symbols. I have a tensor like this one. So what I will do, I will make a matrix. So this direction matrix is very easy. And then I will do the SVD. I will take the dominant vectors. I will put it here. I will do the matricization in this way. So all these three matricization here. Yeah. So one way to make matrix out of tensor is this one. Another way out of this one is this one. And then for the Z direction we can do. Okay. So there are three ways. I will get I will do the PCA, whatever you like, principal component analysis. And first I will get I will do SVD in one of the direction. I will get some PCA vectors. I will use those PCA vectors and do some kind of outer product which was defined earlier, although I skipped it. And then we can make, and then we can do the truncation as exactly similar to SVD, and then we can get our reduced or the compressed tensor here. Okay, so instead of using the all full ranks here, I will use some ranks which is defined by me. So it is one kind of compression. Higher order SVD is one of the major algorithm. Okay. Now there is some issue here because there is no optimality here, and at least we know that we can prove the optimality in first thing. And another thing is that we can define singular values, and this is one way of defining singular values, just equivalent to the matrices. Okay, so we can do find singular values. Second thing, I have to find another singular values, but there is a problem because I can go. So for example, I can go in three different direction. Okay, so here first singular value I got is, let's say, x1, x2, x3, some singular vectors. Now I can go direction perpendicular to this, and perpendicular to this. All of them will leads to same different answers, but different singular values. So in the second step, I have three different singular values, and then another step I have 3 into 3, 9, and then exponentially rising. So there is no perfect way of doing this compression for tensors here. So we tried different things. We are going in some direction, and then we are taking, for example, in this case, we are just taking the so out of these three, I will take the largest one and then proceed in this direction. I will take the largest one and proceed in that particular direction, ignoring rest of them. Okay, so now you can see that if I ignore something, there is a problem. But all HOSVD and doing this kind of some traveling thing and all those things, I get some results. Okay, and those results I will show you. But now there is a problem. When we tried this one, singular values, we got some strange answers. Okay, and strange answers were mostly just because there was no convergence here. So we tried to find where it will converge and all those things. So we keep on doing it. Later on, we realized that convergence requires some kind of special operations. Okay, some kind of uh, iterations here. So Jacobi iterations, we used to say that, and then we can prove them. Okay, so for example, we did it and we proved that this how we can get the singular values here. Okay, so the results which we got were very good, means it is converging, but sometimes it is very slow. The convergence were very linear here. So now let's come back to the compression. Okay, so this was the original thing. Please, a lot of theory I have explained. Please uh, do not worry about it. Okay, so you just see this one. Okay, now what I am doing here is I am just retaining only. So out of this 262, I will retain only the 15 component here, 15 component here, and 15 component here. Okay, so now because it is three-dimension thing, compression means 99.79% of the data I will remove, please, and just check what is happening. So please remember that 99.79% means I am taking less than, means half of the percentage of the data, but still you can see that things are working. Okay. Okay, so this one is original. Okay, and this was the algorithm which was proposed by someone else. and this is HOSVD. And these two algorithms were proposed by us, and you can clearly see that it is giving good result. But still, in my experience, after so many years, I never recommend that use my algorithm. Please use the HOSVD. It is very consistent. Ours is not so consistent. Okay, but you can clearly see that even removing 99.79% means it is just 0.21 percentage of the data. We can recognize the face, please. Anna. So we can see one more time that what is the original. So taking very small amount of data, please. Anna. So the compression percentage is very high, 99.79. You can clearly see that still we can identify that some identification is there. But if I obviously increase this uh, or decrease the compression percentage, I will get better clear results here. Okay, Meena sir, how much time I have? Let me check. Okay, I will try to wrap up in 20 minutes or something. Okay, 15-20 minutes. Okay, so this basically shows that okay, this is the previous algorithm. So probably you cannot see it. So the error is very high, and the green one was this MVSM, and these two are little bit of comparing size, but
कैमरा ऑन करना
Sir. Hello.
हाँ
Hanuman sir, so actually, sir, right now we can have a break for some time.
okay, okay.
Yes, sir.
We will come back in 10 minutes or
Very
so.
intense session, intense deep learning session.
Okay.
So see, for the participants, see, just we have a break for basically 10 minutes. So we will come back at 4:15 or even then 4:15 so that you can have your question answer sessions with just we will meet at 4:15 and yours are 7:45 p.m. in South Korea. Actually, Professor Hanuman, South Korea, so yours are 7:45.
Yeah. Okay, I will come back at 7:40.
Yes, sir. Okay.
पहले नोट तो ठीक चल रहा था कल से प्रॉब्लम हो रही है प्रॉब्लम चल रही अब तो आज वैसे भी कुछ नहीं हो सकता फिर उनको वो भी क्या ही करेंगे मैं ट्राई करके देखता हूँ एक बार
So, sir, how is the weather in there? You in Seoul? So, sir, in which town you are there?
Oh, I am near Seoul only, but weather
So,
is at present like our February of Rajasthan.
okay, sir. So, we welcome all our speaker as well as participants to rejoin the session.
Shall I start?
Uh, just okay, I think, sir, you hand over to you.
Okay. Okay, so next thing is very simple. Now we want to use this tensor thing in neural networks. Okay, so that's a very interesting thing we have to do. But how to do this one means why we want to do it is very clear that if some of the data format is in 3 dimension or 4 dimension or more than that, we want to represent in terms of uh, uh, tensors or multilinear algebra or whatever way we have seen. Okay, so now this is there. Now I have done that, but the problem is how to use a neural network here. Now this is a little bit complicated situation, but the main advantage is that when we use this tensor factorized neural network, we get less number of parameters, and this less number of parameter is main aim of machine learning. All of machine learning which we do, it totally depends upon how many parameters we are having and how much data we are having. Now if sometimes we have sufficient data available to us, but uh, uh, data is available, but the problem is then the algorithms, they do not support. Lot of algorithm problems are there. Sometimes uh, parameters are more. If we have big network, but data is less now. So this type of issues are there. So now uh, number of parameter, less number of parameter is one of the aim in machine learning, and this is what we want. So for example, CNN is also introduced because of this particular motive. Okay, but let's see how tensor factorized neural network works. Okay, so it's very easy, not very hard. So okay, so we have a tensor. Now what I will do, I will multiply three sides. So assuming that it is a three-dimensional thing, all three sides are available, I will multiply with three different matrices. Okay, and I will choose this matrix set in such a way that matrix multiplication leads to a smaller tensor. Okay, so now this is the situation. Now the main thing is we do not know how to decide U2, U1 and U3. Okay, so this is a problematic thing. I have this thing, I do not know this one, I do not know anything further than that, but I want to identify U1, U2, U3 in a way that uh, my error criteria is minimized or something like that. Okay. So now what we do is that we, instead of looking or choosing earlier in HOSVD or the SVM and the algorithm which I have shown you, we used to choose this U1, U2, U3 by some method. Okay. And I do not know whether it is perfect or not. But now what I will do, means by this error minimization, I will identify this U1, U2, U3, basically optimization, but since it is a data and some uncertainty is there, and we can use machine learning methods here to get an approximation of U1, U2, and U3 here. So basically learning of this. So what when we do that, we want to identify U1, U2, U3. In machine learning language, it is basically known as learning of U1, U2, U3. Okay, so this particular thing is one thing, and then it is passed through your nonlinear function. Okay, so this is entire tensor feed forward layer. Okay, now this layers, so this is my first, I mean, data matrix. I pass through, means whatever same format, and these layers are designed in such a way that they can take this input, please. And so please remember, so this this is the input. So layers are designed in such a way that it will take this input. It will go to this one. You will get a smaller tensor here, smaller size tensor. Now the next layer is also designed to take input as tensor, same thing. Okay, and then the same means decide upon your nonlinear activation function, and then keep on repeating this, how many layers you need and all those stuff. In the end, what we need? In the end, we need probabilities. And how to get probabilities? We use the same idea which we used to do in uh, ANN, artificial neural network. We will do an inner product with a weight tensor. This weight is also we will learn. Okay, we will do inner product. So when we do inner product of tensors, what will happen? We get numbers, if you remember earlier. And when we do inner product, we get some numbers here. And those numbers, now we have numbers. Now how to convert these numbers into probability? It's very simple. When all of us, you know the answer. What is the answer? You pass through a softmax layer. Okay, so this is what uh, we have to do. Okay, and error criteria totally depends upon our application. It is analogously designed, means you can use least square, or in case of classification, you can have cross entropy. Okay, so now just a very simple example. So we have speech signal, and we have applied it to many applications here. So in a speech signal, uh, um, this was related to emotion recognition. Okay, so we applied, we take Mel spectrogram, both frequency and time domain information, mainly because we do not know where emotion information is there. We want to classify basically four basic emotions: angry, happy, sad, neutral. And then we have taken the delta, mean the just difference with the neighboring one in the row side, and the double data means double differentiation. And then we get this thing. I arrange them in a three-dimensional manner here. So I got my tensor. So now we applied this TFNN, and we want to see what is the result here. So you can see here in the so I mean, this is the untrained distribution. Okay, so for example, angry is red, happy is green, and neutral is blue, and sad is this is some color, I mean indigo probably. I mean, no, I mean, it's some dark blue or some kind of some shade of blue. Okay, so these two, there is not uh, much overlap is there. Okay, so neutral and sad. Okay, so there is some, naturally there is some demarcation there, but this sad is mixing with happy and angry, but the overlap between happy and angry is huge, means you can see here. Okay, so just see green and red dots are intermixed with each other very nicely. Okay, and why it is very easy to see also that sometimes means for us it is easy to identify, but if it is cultural or something, or if it is in a different country, it is sometimes difficult to identify that whether person is angry or happy, and for computer it is more difficult. For example, the same word can be said in an angry manner or in a happy manner by yelling. Okay, so now it is very difficult to identify that. For example, when we say that yes in happy tone, yes, and and in an angry tone, that yes. Okay, so both of them are same word, but slight uh, uh, change is there, which human can identify easily. Easily means in with better accuracy, but for machines it is very difficult to identify angry and happy. Okay, so now what we have done, we applied some traditional method like CNN, LSTM here. Then you can see that this neutral and sad is clearly they have demarked it, but this angry and happy is still mixed. Okay, and it is a difficult problem, please. So this sad and neutral is not a very difficult problem. It is evident from the untrained data, but some mixing was there, and the CNN LSTM is able to identify the differences here. But you can clearly see, try to please have a look here, that this angry and happy are totally intermixed with each other. Now what we did is that we applied some especially some attention mechanism and all those things, and then we identified, and you can see that still angry happy is there. They are little bit mixed, but it is not as mixed as here and here. There is some better classification we can see here when clearly have in this boundaries are there for sad and neutral, then happy, and some kind of boundary like this one. But TFNN, you can see that it is doing little bit or much better task than this particular sorry, tensor based neural network. They are doing much better task than CNN and LSTM. Okay, and it is only because and there is another advantage here, that we use very less number of parameter. Number of parameter, I think I do not have that data here, but we are doing with very less number of parameters here. Okay, so that's the advantage of using tensors. So I just want to conclude now that uh, please take home thing is that we have to represent our data in natural format as much as possible, and especially in three-dimensional case, tensor helps in large compression. We have seen that it is almost I mean with just retaining only 0.2% on kind of data, and we were able to see something there. Okay, and another problem is that this problem is little bit difficult because we do not have a perfect definition of tensor ranks. With matrix we have a perfect rank definition, but we do not have for tensor. uh, this I think I just skipped it, but we whenever we want to do the compression case, I will recommend use higher order SVD. Okay, and there was some numerical issues which we have removed from that one. That is only for those who are mathematically inclined, and this is basically is the main thing, is that we can use tensors in neural network also, which helps in reducing number of parameters in training. Okay, so that's what I have. Thanks, and visit Assam whenever possible. Please let me know. Okay, thank you. If you have any questions, please ask me. So if you have any questions, please let me know.
So To the participants, please type it in chat box. I will pass on it to Professor Hanuman.
Oh, there is a chat box.
So Krishna is asking, please explain how the distribution of features is plotted on one of the slides, showing better distribution with TFM.
Okay, so ma'am, this is something still under investigation, that why tensors are giving better result in this case. Uh, 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 this is, please, we do not also, so just to prove our point, we use this particular diagram here. But again, we are still researching on this one, that why tensor is giving better result. One thing which it's just a postulate, please. So from science point of view, there is a postulate which we are trying to verify, is that this emotion information is in between frequency domain and time domain and various other domains which we probably do not know. And tensors, they retain this time and frequency information in natural format in a three-dimension format. For example, speech, we do 20 millisecond. For 20 millisecond, we have a Mallet spectrogram. Then another 20 millisecond, we have another Mallet spectrogram there. So that natural order is maintained. So most probably this is the cause. But again, please, since we are not able to prove it, I just want to say that this is the postulate.
Sir, can you recommend any basic exercise those people who are new to start with this tensor or
Okay, so there is a paper by Kolda that tends. I will write here. So
yes, it's
my
because
so my
for many
email.
students it may be a
So mathematically, this author name is Kolda, and her tensor papers. There is a review paper, tensor, and so one review paper is there by Kolda. So that is good
cold.
for. Yeah, Kolda is the author name, and her tensor papers are there. So for these papers are good enough, and my email ID is also there. So if you want
Yes.
to use them and you are not able to understand, or you require some help in understanding, please, my email is there. You can always contact me.
So here one of the main question is that as you, I am very new to this tensor. I have never used it and should be in the same position. So it seems that we have means when we use for the image compression or for the some deep learning, means sometimes for the where do the position of the tensor and it is where
Oh,
is
I
the
am not. Sorry, I am not able to
okay.
hear. I think there is two, three voices continuously, some kind of echo, or I do not know
Okay,
what is
that's
happening.
so sir, what I'm asking as a very layman person,
Hmm.
what is the prime need of using basically tensor, and how do we evaluate yes that tensor
Oh, okay.
in on which scale do you measure that yes my paper is better in tensor than the another one? You have just shown the one paper where you are showing the emotion recognition from the speech. You have compared your some tensor work with the CNN LSTM.
Hmm.
So what is the layman picture?
Okay, so basic thing is that first we have to identify that how my data is represented. Okay, so for example, your data is one dimension, then I will not recommend, because and if it is two dimension, then CNN you can use. But if it is going,
Okay.
your data is going in multiple dimension. Okay, so three dimension or more, then first time means we have to think about tensors. Means that is one of the thing which we should be aware
Okay.
of. And
Okay.
another thing is, when we go in multiple dimension, the problem is that our data increases exponentially.
Mhm.
Okay, so and if you, for example, you work in video processing and all those things, you need lot of computational power, and uh, or better means you can say fast processors to do this processing very, you can say, efficiently in machine learning, especially to or to train also. It's not a very easy task, especially in multi-dimension going beyond three or more.
Mm.
So their main aim is not like, okay, this CNN is there or something is there. The main aim is little bit shift is there. Means we can do it with CNN, because I told that videos we can just divide frame by frame and then we can do, or some kind of other algorithm. But the main aim here is, one of the aim is to do the accuracy, means that is always there. But another aim is that we have to train as means in, you can say, with less number of parameters and all those things. So sometimes what we have, or the situation is like that, the data is little bit less, and because of this video and the exponential increase in data, number of parameters are very high. Okay, so data is less, parameters are high, then we will be in trouble. Mean that is obviously, if we go by simple rule that
We can't
more
find out
parameters.
of the data.
Mm, so that is the basic thing. But if your problem, or if our problem is just one dimension, two dimension, do not worry about this. This worry comes only when we have higher dimension means in the data.
Oh. But sir, here when you are basically using it in the speech recognition, speech is a I think one dimensional data only.
Uh, uh,
From
that
the
is the
talker
problem.
only. Yeah.
So what happened is that we started with one dimension. Then the issue is that this emotion information we do not know is in one dimension, two dimension, or three. So, for example, uh, when I say angry in an angry tone, that yes, okay. So now the entire information is there in the time direction, but there is some frequency modulation also I am doing in my voice. Okay, so some kind of frequency information is there. Now this time and frequency both are there. Now it is and then I have several segment for the same person, and little bit bigger word is there, or bigger sentence is there. So we started with one dimension, that information, when the emotion information was not we are able to capture. Then two dimension we are not able to capture. Then we went for three dimension, because nobody knows where the information lies, means where is this information in my speech, you know? So that's why we have to go to three dimension in speech.
So here, sir, you are considering it speech as a three dimensional. Is it so?
No, no, no. I am not considering at three dimension. I am making my data in such a way that uh, it captures all possible combination, or all possible things. In, for example, I need time and frequency. So both information needed two dimension is there. Now this time and frequency plot I have only for 20 millisecond. Then for next 20 millisecond I have another time frequency plot. So you can see that one time frequency plot. Then next 20 millisecond, I have another time frequency plot. So basically, it's a video, na? So frame,
Okay.
so frame 20 millisecond, one frame, 20, next 20 millisecond, another frame, next 20 millisecond, another time frequency plot. So that leads to a three-dimensional data. And we went there just because one and two dimension was not working. So that's means I agree with you that if we have to start with simple thing, and later on when results are not perfect, then we have to increase the dimension in a way that it naturally retains the properties of the original signal.
And sir, what about its application in the basically that this we say MRI images also two-dimensional. So have we possible using tensor there?
MRI I use only for compressions. So for
Okay.
compressing the MRI data, so that can be done using this three-dimension or tensor compression algorithms.
So tensor compression is used there.
Tensor compression is used there. No neural network there.
Okay. So I think that its application would be in the video only mainly because
Mostly video.
mostly. So any other question from the friend side? See, please feel free to ask it. See, generally we have the notion that I need to be expert. My question must be good one. See, please leave all these formalities. First, when very basic thing, am I able to gain any one point from the lecture? Then the second point, it needs to be the beginning. Always be like a learner. Don't overimpose any expectation. So I'm waiting for participants. Apart from Krishna, Joseph, Ritesh, Devashish, Karthike, Snehal, Suman Paria, Suman Rekha, Vimal Prakash. I hope you would be there, not uh, your mobile or your laptop only.
But in any case, it's not an issue. They have my email. Please, if you do,
Huh?
please have my email. And if you feel there is some application you can always discuss with me. Krishna madam, I think I know Krishna madam.
She's asking, are these simulations done in MATLAB or Python?
Compression I have done in MATLAB, and uh, this neural thing was in Python.
Oh,
So we wrote our own libraries for this neural network.
okay. Suman, but that we can. It's heavily raining in Kolkata. I'm unable to listen. I think you can transfer some rain to here in Rajasthan. No problem, Suman. But thank you for your patience that you are still listening and that my student is there, Anand. He is interested to know about South Korea. You are planning to visit Assam, but Anand,
Hello, sir.
your company is good.
Hi, hi Anand, how are you?
Fine, sir. I'm PhD scholar, sir.
Oh wow. I
Sir,
have
actually, I'm
to.
asking how much data is required to run the CNN or TensorFlow?
Oh, this
Hello?
is a very subjective question. Means I have no perfect answer for this one. Depending on application, I can say answer. Totally depend. When I always say in the sense that you should have. So, for example, just learn from our school days, no? So, for how many equations? I mean, for let's say three variables, how many equation you need?
Sir, three questions. Hello?
I mean, sorry, three. You need three equations. So, in case of let's say I have 1,000 variables or parameters, then I need 1,000 equations. So, 1,000 equation means
Okay.
1,000 data points. Now, 1,000 data point is not enough because in linear algebra, you know that this may leads to no answer or something. There is always so at least so there is a problem now. We should have many fold means I will say 10 times or depending on the application it can be little bit higher, but it should be multiple of the number of parameters which you are doing. And this is a very crude thing, please do not think understand how do this type of thing. But one data point and independent means it should not be like that same data point you are repeating many times, please, you know? So many data point means so those equation thing is our school type thing, but to because for probability theory to work we need large amount of data. Now this totally depends upon application, man. And
Okay, sir. Thank you, sir.
that probability theory works means also sorry,
Hello?
you are able to listen.
Yes, sir. Yes, sir.
So,
Okay, sir.
but for probability theory to work, it totally depends upon the convergence. So, so once you have convergence kind of thing, then it is fine. Otherwise, perfect answer totally depends upon application, please. But one thing is very clear to me is that no, our data should be multiple times of our number of our parameters.
Sir, one question is there. Krishna is
Mm.
asking, sir, we interacted once during my PhD days. Krish,
That's why I know Krishna madam. Mhm.
Krishna, madam, from where did you pursue the PhD? At MNIT Jaipur or yes, I think in the EC department under Professor Tarun Verma. We met. Krishna madam is very active participant in our workshop. Even in my last workshop that we conducted around 2020, she also attended. I think correct? Huh? Yes. K.K. Sarma sir and Tarun Verma. Yes.
Mm.
Okay. So we have its own guide. Professor K.K. Sarma. Good. So where are you working, Dr. Krishna? VIT. It is VIT where? It is Bhopal. Very good. So you can note down the email of Hanuman sir, and you may also. So, sir, what type of other scope is? I think it seems that you are working in deep learning. What can be done at the research level in this field? Because usually people feel that you need to uh, enter the layers and not see. Normally, there is a one contradiction. People say it's very easy to publish in the deep learning, but when you go to the deep learning, understand the deep learning, it's only layers, minimizing the layer, etc. So, is it really true that it can be easily published? And if it can be easily published, then what is the crux actually? Because tensor topic comes from the root of the deep learning only.
I normally work in a little bit mathematical side of this deep learning and all those things. So for me also, it is not easy to publish paper. But uh, yeah, if we publish on a very innovative application, so there are means I have seen two type of thing. One set of people, they work on data and making, I mean, collecting data and using it for some innovative application. Okay, so that is one of, it's mostly modeling kind of thing. Another set of people, they work on mathematical side of this deep learning, trying to develop new architecture and then apply it for some particular problems, which is very suited, or it is designed especially for that particular application. So these two type of things are there. Now, means we can publish in one of them, but any, for any paper to have perfect result, just Anand said, na, we have to do a lot of work. Means we do not know when convergence will happen. In probability theory, all of us know the central limit theorem and law of large number and all those things. But when they will start showing the convergence, that is, it totally depends upon the application or the problem at hand. So we can prove some of the convergence, but just one answer for everything is not possible in machine learning or deep learning. So that's the thing. But some of the fundamentals we can learn, means there is no. For example, I always suggest my students in working in deep learning to have a good grasp over law of large number and central limit theorem. Once we know this theorem, at least then we know that, at least we know when to expect convergence, and what is convergence we will learn from that. Otherwise we will keep on changing this thing, layers and all those things, and we do not know where we are heading towards. When just little bit understanding or a good understanding is, I mean, is needed for uh,
Okay, so
I'll
thank
say
you.
it is better to learn a law of large number as good as possible. Means.
Suman, Suman Rekha, can you? Okay, sir, I think there is no more question from the participant. It's a very nice session that
Okay.
you have presented. This year you introduced this concept. Even it is the first time that I'm going through tensor. Even I asked Hanuman sir that whether sir is it how Suman is asking how to handle lot of noisy data generated from IoT sensor. It's written in chat box if you can see. Someone
Okay.
is from Jadavpur University. Someone
Okay.
Varia.
This is probably not my area. I haven't worked on this one. Probably you can answer better than me here.
Someone see when it is coming to the basically noisy data generated. So here see there you can handle again see you will apply basically the filter only means pre-processing suitable pre-processing you will uh, use that means can we do any some common normalization or we can use any filter can we take out the mean variance etc so that can be done because data once data has been generated then it can be addressed that how means are we able to detect out the which type of error is there which type of noise is there so that's basically in the comes under the pre-processing it can be done and more particularly depends upon suitable application specific application because IoT sensor is very wide scenario. So from the given set of the data, you have the knowledge type of noise is present and how to minimize it during the pre-processing. So so when you sir do the work in mathematics, so how in mathematics is it again programming based or you how do you set? Can you give example of any basic problem where you have worked upon? Very basic one, so that it can give the idea that what type of approach do you use.
हाँ, वो म्यूटेड है, म्यूटेड है सर उधर से आवाज नहीं आ रही, बोल दीजिए वो म्यूटेड।
Oh, okay, sorry.
Sorry,
So very basic problem, for example, is that how to go beyond Nyquist sampling, and this type of work I have done.
okay. How to okay? It is basically double. Nyquist means it's a double of the highest frequency.
I mean, we cannot. I mean, Nyquist sampling rate is there, but can we do better than that? Uh,
Okay.
because Nyquist sampling rate is only for band limited signal perfectly, means it gives zero error.
Hmm.
So
Yes.
now nobody knows that if it is not band limited, then what is the perfect answer?
Hmm.
So that answer now people know that, but in various scenarios, for example, uh, some kind of situation where it is a mixture of you can say continuous signal and discrete signal, and then uh, downsampler is there. What is the optimal or the best possible answer in those type of settings? It is sometimes some, so those type of things requires pure mathematical optimization answer. So that type of problems I work upon, and here in deep learning, mostly tensors, which I have explained, but some other problems also, which I am learning now in Korea.
So I think we can conclude the session, sir. We are really thankful for your giving the insight in this new topic to everyone. Um, Thank you. Yeah,
Okay.
a very good
Okay.
evening. Okay.
Thanks.
Okay.
And send Anand to Guwahati once, hai na?
Anand was saying that in going South Korea, it may be a problem
Uh,
because family-wise, because it's how is the country, etc. But Assam, he can come.
Most probably I will come back in December so he can join me there.
Assam, so it will be a 6 month visit,
8 months.
8 months, and there only.
There in the same place. And then
That's
in January I will be here. So then Anand can visit us, please.
okay. Okay. So it's a focus perfectly.
Okay.
Thank you.
See you. Bye.
Thank you.
Bye.
Yes, say bye, sir. Okay.
सर वो मुझे वो बंद करना होगा
Or so to the participants.
Pad- pad स्क्रीन बंद करना।